talk to you about what led up to us creating our own laptop. We're going to go into a little bit about some of the decisions we made, and then we're going to tell you about what we're actually doing with this laptop, what the strange requirements that we've built into this, how those have actually helped us. So to begin with, both Bunnie and I have wanted to create our own machine from scratch for a very long time. Bunnie's first machine was an Apple II back in 1983. My first was an Amiga 2000 back in 1998. And from these beginnings, these old machines included schematics in the box. And that's something we've lost since then. Fast forward another 10 years, in 1998, Bunnie actually built his first single-board computer, a self-contained, it was an SH1-based data acquisition platform, kind of a hacking type thing. That was his first foray into actually building his own. It wasn't a laptop, it was a single-board computer that you could do interesting things with. In 2006, Chumby came on the scene. Both Bunnie and I used to work at Chumby. And when Chumby first started, most of the time and effort was spent actually getting the product out. However, we did manage to slip in a few Easter eggs that were very conducive to adding a laptop. The original Iron Forge Chumby, which is what this is, if you turn it upside down and open it up, there's actually a 9-volt battery outlet on it. You can plug in a 9-volt battery and actually run it without a cable. It didn't work very well, it only lasted about 10 minutes, but it was a laptop of a sort, a nice squishy laptop. Okay, that didn't work very well. The Falcon Wing was the next generation Chumby. This one actually had a battery charger, so that became a feature all of a sudden. And we upgraded a few other things. We had a USB 2 port. We replaced the internal flash, the cheap small flash, with an SD card that had a lot more space. And this led us to a couple of interesting hacks that were, again, brought us a little bit further on the road to having a self-contained laptop. One of the things we did was we ported a compiler to this. So suddenly, this little Chumby that we had could compile its own code. And with the battery, that meant you can compile your own code anywhere. And we added an Easter egg that makes this, I think, the easiest machine in the world to get root on. What you do is you plug in a keyboard anywhere, no matter what the machine is doing. If you plug in a USB keyboard into a Chumby 1, a root console will actually drop down from the top and let you enter all your commands. And this actually came in handy a few times. This came in handy, particularly in China when we were trying to debug the software, because if the thing's not connecting to the network and it's all buttoned up, having root console access is really useful. Another hack that we had on the original Chumby that was conducive to us actually using it was we had a 3G router. If you plug in a 3G dongle and you create a specific access point, you can use it as a wireless AP, kind of like a MiFi type thing. After that, we went on the Silver Moon, which is basically the Chumby 1 that was faster. But the core of the Chumby 1 was used in the NETV. NETV was a lot different from the other Chumbys because we took the LCD out and we replaced it with an fpga, which we actually used a whole bunch. What the NETV does, I'm going to go a little bit of background here, it takes an HDMI signal and will overlay on top of that the contents of the screen. So instead of having a little tiny Chumby screen, you have a giant 42-inch TV or whatever you plug it into. And this had an SD card like the Chumby 1. But as far as hacks that we did, we built this little board you see on the side here. This was our breakout board. It would go from HDMI to one of the two LCD standards. So using this, we could actually run an HDMI cable from the NETV out to the breakout board, and then you could plug it into an LCD. And using this, we designed the very first proto-Novena laptop thing, where we actually had a pixel sheet display. We had HDMI cables running everywhere. We used a USB battery pack, and we had our own little laptop, compiler and everything. The problem was, like all of the other products, we didn't really find much use for it. It was too slow. Okay. It was too slow. And so Bunnie and I sat down after Chumby was done. We were sitting in Singapore, having beers. We thought, let's try designing something for ourselves. Let's see if we can design something that we would actually sit down and want to use. It has all the features that we really want in a machine. And with that, I'm actually going to turn it over to Bunnie. Here, use this.
Hello? You can hear me now? Okay. All right, so yeah, we wanted to design something for ourselves. It was like we had done years and years of work making these embedded systems for like other people that we actually would never really use ourselves, but we were trying really hard to use and sort of failing to use. And you know, one of the big problems is that when you're in a consumer electronics startup, everything is about cost. Everything's really, really cost sensitive. We had like 2-week meetings trying to figure out, like, do we have 128 megs of NAND flash or 256 megs of NAND flash? It's like 25 cents and 2 weeks of argument to try and figure out like how much memory to put in these things. We had to use really old CPUs that were single core, ARM devices. They had no floating point capability, no graphics, no video, nothing. Like, you know, we were living in like 64 megabyte RAM footprints, which actually at the end of the day is really good discipline for making Linux and coding and embedding systems. And Sean's like a master at packing things into very, very small boxes and making them run really, really well. But at the end of the day, like 10,000 years in a lamp will give you such a crick in your neck, right? We wanted to get out of that box and actually like design something we would actually use ourselves. Like we actually wanted power switches on the USB ports, because when you design cost-sensitive consumer electronics, you don't have the 25 cents to put a power switch on your port. You just use the current limiting resistor to go ahead and try and meet the spec. So we decided that we would build something that we could go ahead and sort of just paint with all the colors of the rainbow in, right? Like we're going to put in PCI Express and SATA. We're going to put a real high-resolution LCD that we could use, an actually intelligent battery controller that can go ahead and tell us how much battery life we have to within a minute, right? As opposed to trying to guess and say, we're about like 10%. Oh no, we're at 0, right? Socketed memory, so we can go and upgrade the thing. We want to have an FPGA on this thing, so we can go in and do hardware hacks. A mainstream Linux. We want to be able to like give talks on our laptops. Like we actually want to be able to stand here and actually use our laptop for things that we do. We want to be able to actually make a case for our thing, that instead of trying to live in these small consumer electronics boxes, actually be able to build something that we can use. So we ended up, getting started on this project about a year and a half ago, right? And so as you can see, like it's actually working here. We're using it. Some of the my favorite parts about designing with this is I actually got to be able to do things like design with PCI Express. It's not a lot of these little, handheld like $30 gadgets have PCI Express on the inside, or SATA, or Ethernet. And so it was a good opportunity for me to go ahead and stretch my legs, get myself into some real high-speed design aspects, try to figure out these new standards. PCI Express was very important actually for the laptop, because we wanted to be able to build a laptop that had all the code buildable from source, from the bottom up. And a lot of Wi-Fi solutions require you to load like a firmware blob that you can't go ahead and reverse engineer. And so PCI Express actually had one of the few Wi-Fi cards that had a full open source stack in it, which ended up driving the PCI Express requirement. And along the way, I learned some really surprising things. So for example, the RGM2 is the interface between the CPU and Ethernet. And it turns out that in the spec, they actually wrote in you have to have 6 inches of wire for the clock line, longer than the data lines, because they want you to delay the clock by like 6 nanoseconds or whatever, half a nanosecond, whatever it was, to meet hold time, right? And so there's all these like weird things that you learn about in designing your own laptop and bumping into these problems along the way. We wanted to have a nice high-resolution LCD built into this thing. And so you can see, I love this LCD. You can see how thin it is from the side. Very, very thin. And these high-resolution, new kind of cool kid LCDs all use embedded DisplayPort. It's like what's used on iPad 3, the Chromebook Pixel, and so forth. Unfortunately, the IMX6 CPU that we chose for the laptop only supports LVDS. So we had to go ahead and build an adapter board that went between the LVDS and the LCD. And that was actually, a couple iterations for us to get it right, because the first iteration, we sourced in something from a company called ST Micro, who all the data sheets are NDA. We basically had to call a guy in China who knew a guy in China to go ahead and give us data sheets to even design with it. And then we had to source the components on the gray market. And finally, after all this effort, we were able to oh my God, have a high resolution, nice LCD. And so one of the actually challenges in leading up to getting this laptop completed was how do we get a more open chipset for the embedded DisplayPort. And so we searched around, and it actually turned out that I was in the markets of China trying to purchase the screen. And they have these big open air markets, you can get anything. So the easiest way to check lots of LCDs is go to the gray market and say, hey, show me your LCDs. And the guy plugs it in, demos an LCD to you, says, no, that's not good enough. Plug another one in, showing it, no, that's not good. Well, this looks pretty good. And the box he was using to demo it to me had this very chip on the inside of it. And so while he was demoing it, I just took my camera, took a little picture of it, brought it home. Sean did a little Google search on it. We're like, oh, this chip. And then we found it, and it was totally, it had the documentation, all that sort of stuff. So that's how we ended up discovering this chip. Another thing we built into this was a fairly fancy battery board. The parts cost of our battery board is more than the chubby one, right? So that gives you an idea of how fancy this thing is. It runs its own OS, Chibi OS. It has an ARM7 on it, but the great thing is this thing gives us very precise charge measurement. It has a Coulomb counter, gas gauge, it does impedance tracking on the battery, so as the battery starts to degrade in terms of lifetime, it goes ahead and derates the battery, makes sure you don't overcharge it, and actually computes the total lifetime of the battery dynamically as your battery evolves through usage. Which, because this battery controller had all these smarts, we could actually use really cheap RC car batteries for the battery pack. So you can see on the inside here, this is just a standard sort of Turnigy RC car battery on the inside. And the battery controller itself would go ahead and plug it in. You go through a full charge cycle, full discharge cycle, and when it sweeps across the whole range of the battery, it figures out what the actual capacity of the battery is. Turns out these RC car batteries are really awful. It says 3,000 milliamp hours on the outside. The controller's nah, it's more 2.2, 2,200, but at the same time, these things cost $15 or something like that, whereas laptop batteries typically cost $150, right? And another little Easter egg we designed into this is actually an analog output to drive an analog meter for the amount of current that's drawn. So we haven't built it into this case because all the analog meters turns out are really, really thick. But I thought it was really cool to be able to have a little panel meter, so when you're compiling your code, you can see it actually going higher and higher, or lower and lower, whatever it is, as opposed to the digital readouts. Another thing that we did on this is that we designed the DDR memory using an SODIMM. So this is this socketed memory that you see here on it, which is a little bit unusual in the embedded space, but very common for laptops. One of the reasons we did that is that DDR3 memory is a commodity. It actually kind of trades like oil and corn and all. So there's an exchange for it. There's a daily price, a spot price, a contract price, all that sort of stuff. And we're not traders, right? We don't want to be in the business of dealing with the DDR3 tycoon in China to buy this stuff. It's much easier if we go ahead and put it on a slot, and we just buy what we need when we need it and put it in there. But it also allows us to do things like put almost 4 gigs of RAM in an ARM system, which is kind of rare these days. But getting as much memory as we can fit into a 32-bit address space is very helpful if you're trying to compile code, trying to do development natively, and so on and so forth. On the downside, it was a real pain in the butt to design with. DDR3 runs at 533 megahertz, has a very complicated calibration sequence. It's actually, it was a lot of effort, but at the end of the day, I think it was worth it. So, a little bit about the case of the laptop. It turns out that if you were to build a conventional clamshell laptop, like the kind that you expect, the tooling costs, so that the cost for the molds and the steel things to do it is over $250,000 for that alone, right? And so, and it's close, right? You can't access the internals of the keyboard, blocking the board, and so on and so forth. So, when we thought about how to design the case, we first want to make it very easy to access the internals. So the laptop case, goes ahead and opens itself for you. You don't have to have a single screw to go ahead and get at the main board. You can, it's very easy to hack, and we also managed to reduce the tooling costs and the upfront requirement to do it, so we could actually fit the whole project within a reasonably sized crowdfunding campaign. That was another big requirement, and that's how we kind of ended up at this particular design point. And the other thing I really like about it is that this case is very usable in economy class. The keyboard is detached from the screen, so when you're cramped up and cooped up in sort of economy class and you're up against like the tray table, you just put the keyboard down here, you put the display right here, and it doesn't matter if the guy goes ahead and brings the chair down right into your laptop. Your hands are comfortably out by your knees, the screen's like right here, and you can go ahead and use your laptop. There's a picture of me that I got sitting in economy with the laptop over there. One of my favorite features about this is the FPGA, the field programmable gate array. Does anyone here even know what FPGA is? Raise your hand. Oh, good. Holy cow. That's like the first I've ever seen like everyone raise their hand and know what FPGA is. So yeah, I mean, it's basically like the ultimate hardware like hacking primitive. It's a sea of, you know, gates, so you can wire it up with code, and then it has pins that can go ahead and be configured for all kinds of I/O standards and whatnot. And so we actually break out a whole bunch of the I/Os to a high-speed connector that's capable of about a gigabit per second per pin. You know, back in the day when we were hacking with the NETV, what we would do is we would actually take the HDMI output and we would repurpose that as our sort of like hacking port, because that's all we had. Now we don't have to do that anymore. We can pick our own like proper high-speed cable with a lot of pins and so on and so forth. Originally we had this idea of making the connector Raspberry Pi compatible, because we thought we would just like go on the Pi shields. But then we really realized that wasn't using the full capability, because the Raspberry Pi connector isn't capable of the high-speed stuff that we want to do. We also built the FPGA so that it hangs off the CPU on what's called the EIM bus. It's kind of like a ROM-style interface, so like static RAM or the old-style ROMs. And so it's actually very tightly integrated with the CPU. It just shows up as a memory map device. You can go ahead and map to it with KMIM or direct chip selects or allocate kernel memory slabs and talk directly to the chip. So it's very tightly integrated into the Linux system. And we also hung off of it a 256 megabyte DDR3 memory buffer of its very own. So that when you're going ahead and doing like high-speed data trace capture and so forth, you can go ahead and get very deep traces without loading down the CPU, and you can do computation completely parallel to it. So some of the things that we've done with the FPGA, for example, is we built a NAND emulator with the FPGA. So here you can see there's a flexible circuit board. So that kind of beige colored thing is wafer thin. It's very thin, right? And what you do is you pull off the NAND flash, you solder this underneath the NAND, and you put the NAND back on top. And so this thing will go ahead, and the FPGA will go ahead and listen to the NAND transactions as they're going by. It can log them to its memory. So you can go ahead and, if you're trying to hack something, you can see all the accesses going by. Or you can take off the NAND, and the FPGA can go and say, hey, I'm the NAND. I'm going to go ahead and emulate it. So this is really cool when you're trying to go ahead and figure out what's going on inside of a microcontroller that you don't know anything about, because as the microcontroller is writing data to it, you can go ahead and see what's coming in, tweak something, and it reads it back and get something different. It's a really sort of very flexible, powerful interface. Another thing that we did with this is that we went ahead and built an oscilloscope board that we can go ahead and plug into the expansion slot. So the oscilloscope board itself has like a 1 gigasample per second dual channel A to D converter, right? And so this is where we're really using the full capability of that high-speed expansion port and all the differential pairs that we break out on it. We also designed it so that we're using active probes from the very beginning. A lot of oscilloscopes, when you get them, they have these passive probes, like made out of unicorn hair and unobtainium. I mean, if you think about it, like you're taking like a 500 megahertz signal, you're passing over a cable this long, the impedance is like 1 mega ohm and 10 picofarads of load. I mean, it is the most amazing cable ever. We are not going to be able to source those. So instead, we're actually using standard SATA cables, which come off of your hard drive. They have a lot of bandwidth in them, but in order to use those, we have to put the amplifier right in your hand where you're probing. So we went ahead and built a set of active probes that work with this. And the result is that the signal quality is quite nice. This is the little trace you see there is us probing a USB full-speed transaction. You can go ahead and see it's got nice sharp rise times. You can see a little bit of ringing artifacts. You can see where the bus turns around and the transmitter goes to the receiver, talking, and so on and so forth. Like it's actually, I'm really excited that we have basically this battery-powered oscilloscope inside the laptop. I no longer have to carry oscilloscope and laptop when I go to China to debug stuff in the factory. I just carry one box. You open up, the cables are spooled on the inside, you pull it out, and you go ahead and do your work. And then you also, and at the same time, by the way, there's your embedded development environment, your coding for all the code for the thing you're making. It's like it's a one-stop shop for everything you need. So another thing we decided to bring out there is a general purpose breakout board. So as part of the campaign that we're running on this laptop, we're offering this as actually one of the rewards to the backers that have helped us get to this point. And we thought it'd be just great to have a bajillion GPIOs. Why not, right? Because a lot of people, it's great that we have the high-speed connector, but you have to be able to lay out a circuit board. You have to be able to, actually fab these things and solder these fine-pitch connectors on it. So we went ahead and built a little breakout board. It has a 40-pin, sort of the standard, sort of old-school IDE header on it. So that's a very common 0.1-inch format. You can get the super high-speed stuff off it, but if you just want to go ahead and control a servo motor, it's perfectly fine for that. If you want to go ahead and control LED strips, you can control a dozen LED strips of this all at once, right? All this sort of stuff is slaved directly off the FPGA. So if you need 12 high-precision PWM channels with like 10 nanosecond resolution, you can go ahead and have those, right? That's a bit stream file and this board. So we also put on this board a 6-channel, well, it's 8 channels, but we only break out 6 pins of it, analog to digital converter. So if you want to sense the temperature or see what the current is on something, you can use that. And we have 2 digital analog converters as well. So it's sort of like nice, sort of convenient. I want to be able to turn on off my coffee machine from my Linux laptop and go ahead, wire it up, put it on a solid-state relay, and boom, you're turning off your coffee machine. You can run a cron job, and you have hot coffee in the morning, right? So this is sort of the little box of chocolates that you get with the device. So we can take it back to Sean. Hello. Hello. Sean's mic. Testing.
Hello. Okay. What? Does it work now? Good. Okay. Now okay. I also wanted to call out the CPU that we use in here is an i.MX6. It's made by Freescale, and it's very easy to obtain. You can actually get this on DigiKey. And there are a whole bunch of other projects out there that are using the same CPU. So if you're kind of interested in this, if you want an open source Linux laptop type thing, there's a bunch. Here's just 4 examples of other platforms that are using the same i.MX6 CPU. So the same kernel will run on these boards as this boards, and these are, some of them are under $100. So if Novena's too expensive and you're interested in this, check out one of these. And of course, these don't have the FPGA. That's what you get. Because there are so many boards that use the i.MX6, mainstream Linux is actually starting to support this. What normally happens is there's 2 options if you're interested in Linux. When you get a CPU, the vendor will give you what's called a board support package. And it's where they take Linux and they add thousands of patches that add support for your particular CPU. They'll add support for the SD card, for the SATA, they'll add support for all the power regulators. But it's really far removed from stock Linux, and we kind of have an unusual requirement. We want this to be long-term. So what we're doing is we're taking a lot of those patches and we're writing our own patches to add support for Novena to mainline Linux. In fact, this right now is running mainline Linux. We have multi-monitor support. The display you see there is a little bit different from what you see here. And the benefit of going mainline, which is the BSP, is that it's always being updated. With the BSP, you have to wait for the vendor to actually release a new version. With mainline, you just download it. It's really easy. And so by going with mainline, we have super long-term support.
Basically, the great thing is our kernel maintainer is Linus Torvalds.
Yeah, Linus Torvalds maintains our kernel. That's it. Any questions?
Yeah, there's a few minutes left here for questions.
Yeah.
We are still actually running the campaign for these right now. If you're interested, go to crowdsupply.com. You can go ahead and back our project, buy us a beer, buy a laptop, whatever you want to do. So.
And if you have questions, we'll probably stand around over there, or I'll be at the Freescale booth, which is just 1 row that way.
Right. Yeah, this laptop will be right over there. 2 of them are over there, and we'll be around kind of through the day. You can go ahead and touch it, play with it, do what you want to do. So. Thank you.